Hey guys, welcome to a new chapter. So in this, this will be chapter number 3, and today we will start talking about differentiability. Well, in other words, we will be talking about derivatives. And in this lecture and in the next lecture, we will devote this to the main properties of derivatives. We will learn what the derivative is, how to compute derivatives by using the definition or not. We will also see what kind of rules we apply for computing derivatives, and why not? We would like to see how derivatives of elementary functions look like. And also, in this chapter, we'll not just we won't deal only with the computation of derivatives. We will also see how we can apply derivatives in certain situations, such as in real-world applications, or we want like to see more qualitative properties of derivatives and how to use them to sketch the graph of a function. So it will be quite a long chapter. It's a beautiful chapter. I think it's one of the most important chapters in this course. Of course, I will rely on the first 2 chapters on what the function is and on the elementary functions. Also, I will rely on the limits and continuity. You will see that differentiability, well, derivatives will be connected, directly connected to continuity, because here we will take a limit as well, but the only difference is that we will not take the limit of the function, we will take the limit of the difference quotient. And we have seen, I think, in one of the examples that I showed you what the difference quotient is about. All right, so let's get started. And first, I'd like to start, just like I said at the beginning of the lecture, with the notion of the derivative. Okay. All right. So like I said, this will be quite a long lecture. I will not have time to fit everything into just one lecture, all the slides and everything. I will just I'll divide this into 2 lectures. So today and also on the Wednesday's lecture, we will be talking about derivatives and I would say the main properties of the derivatives. Okay. Let me start with what is in fact a derivative. And let me just say if you, let me say something that you will usually learn in a physics class, in an introductory physics class. So let's talk about velocity. So let's forget about the derivative for the moment. And let's talk about velocity. So suppose that a ball travels at 100 feet in 4 seconds. The question is how fast it will go. So that is the question that we would like to answer. And so basically the algebra tells us that the distance traveled is nothing else than the velocity times the elapsed time, right? So in other words, we will have that since the distance traveled is 100 feet, then the 100 will be the velocity times the elapsed time is 4 seconds. So this will imply that the velocity would be 25 feet per second, right? So that's what we will deduce, right? So that will imply this, right? Pretty simple. All right. So this is where we'll, starting from this very simple example, we will see how this will be related to the derivative at some point. Okay. Now I'd like to talk about limits of algebra. And so, well, clearly, as you might expect, that was not the right answer. So that would have been amazing if this will happen. But the ball doesn't travel at exactly, that is the main difference between and this is the word we're looking for. The ball doesn't travel at exactly 25 feet per second the whole time, and this is the word. So, since this doesn't happen, you cannot just do what we did here. So if we had formulated this as, suppose that the ball travels exactly at 100 feet in 4 seconds, and if we asked ourselves how fast does it go, then yes, you can say what we just said, right? We can have this very simple algebraic equations. Well, just like you see, the algebra will tell us this, but usually it's not like that all the time. So since it is not, the problem doesn't tell us that the ball travels exactly at 20 feet per second the whole time. Well, if this doesn't happen, we're wondering, if we know where the ball is at every point in time, can we do better? That is the question. So here is an example. And I would like you to look at this example very carefully. So we have the position, and we also have the time. So suppose that at 41.3, the time is 0.9, right? At 41.3 feet, the time is 0.9 seconds. At 43.2, we have 0.95. At 45, we have 1. And then at 46.7, we have 1.01. And also at 48.3, we have 1.10. So suppose we know this. Well, if we know this, let's see what happens. We would like to see on this example here, keep this data in mind. So 41.3, 0.9. Let's look at this. And let's translate this a bit. Look. So at 41.3, the time is 0.9. So let's analyze this very, very carefully. So between the time t 0.95, right, and t 1 second, as you can see here, between, look here, see between these two, 0.95 and 1 second, the ball travels, let's see, how much does it travel? It travels this much here. It travels 45 feet minus 43.2 feet, which gives us this guy here, 1.8 feet. So at 1 second, so at t 1 second, the velocity is nothing else, is roughly 45 minus 43.2 feet over 1 minus 0.95 seconds, which will give us this, which will give us 1.8 feet over 0.0 seconds, and this will be 36 feet per second if we do a computation here, right? And well, if you look at this guy here, 45 minus 43.2, you see what we did now, right? You see, if you look at this, so this is, let's say, position, look at these two positions here and these two here. So we subtracted the positions, right? We subtracted this minus this over this minus this. So this sounds, it looks like a difference quotient, right? So that's what we did. Well, basically, maybe we just computed the derivative at the time at a certain point, right? Anyway, I'm not going to divulge anything now. So just keep in mind for now that this is nothing else than just is that difference quotient over there. So this looks like, so this guy here, let me just say, looks like a difference quotient. So far, this is what it is. So we haven't taken any limits so far, right? Okay. Well, like I said, can we do better? So let me just divulge it. So if we want to be more accurate, we would have to check the change in position from t 0.99 seconds to t 0.99 seconds, or to t 1.0001 seconds. So everything will be around 1. So this is around the point t equals 1, you see? So I'm taking all these values, which are less than 1, also greater than 1. So I'm looking at the values from both sides, from the left and from the right, of 1. But that's still not perfect. We need the limit. So we need the limit as t approaches 1. And if I would like to go back, I will go back to this difference quotient here, right, as you can see. And I will take, so at t equals 1, the velocity is that. So basically, we need to take the limit as t approaches 1. Anyway, we will be precise. But so far, this is what we need. We need to take, we will have this limiting process that we will need to take into account. Right? Okay. So now let me give an example. And so that things will be very clear. So you see, I have the position functions of a particle is this quadratic function is s of t is 3t squared plus 2. Just look at it, right? And the question is, what is the instantaneous velocity at t equals 1 second? Well, when we talk about the instantaneous velocity at t equals 1 second, we will see exactly that this will mean nothing else than just the derivative of s, whatever that is. We haven't defined it yet. But when t equals 1 second. In fact, I'd like you to think of this problem a bit. And you to tell me, what do you think that the instantaneous velocity will be? when t equals 1 second. So Jonathan says something, okay. See, many people say 5, 5, 5, 5, okay. All right, all right. Maybe you're right, we'll see. Well, usually, okay, okay. Let's see. So that is a question we like to answer. And maybe this will have to do something with that difference quotient over there. So some of you, many of you said 5. All right, let's see. So let's see. Let's do it intuitively first and without bringing any notion of the derivative. So let's look around 1. So let's say between 0.9 0.9 seconds and 1 second, so between t equals 0.9 and t equals 1. So the position function is given by s of t to be 3t squared plus 2, right? All right. And now let's see what is the change in the position. So the change in the position is s of 1 minus s of 0.9. But s of 1, if you plug it in, will be nothing else than just, if we plug it in, let's say here. So s of 1, if we plug this in, so it will be 3 times 1 squared plus 2, which will be 5, right? And s of 0.9 is nothing else than just 3 times 0.9 squared plus 2, which will give us 4.43. So we'll have these two numbers that you see here, right? And now we're just going to take the difference. So the difference will give us 0.57. So that's the change in the position. Now we're wondering, what is the change in time? Well, the change in time, because we wanted to see what happens between 0.9 and 1, it will be nothing else than just the difference between the two. So it will be 0.1 second. So that's what you see here. Well, the average velocity will be nothing else than the change in position over the change in time. So we will have this. So that will be the what we will call the average velocity. So you will just divide the two. So delta S will be the change in position, right? So is this guy here? And this guy here will be nothing other than just delta T. So the change in position over the change in time, which is delta S over delta T, will be 0.57 over 0.1, which is 5.7, right? All right, so this is how we compute the average velocity, right? This is how we compute. So in other words, the average velocity will be the change in the position over the change in time. So that's what you need to know. All right. Now let's see what happens similarly. We want to see a similar situation. So keep in mind, it's the result here. So this is 5.7. And now we would like to see what happens with the average velocity when we will have something a little, even something very closer, but still around 1. So when we will have, we would like to see what happens between 0.99 and 1 second, right? So we'd like to see that. Well, again, for the same function, so between 0.999 and 1, the change in the position will be s of 1 minus s of 0.99. So it will be, again, s of 1 is 5, and s of 0.99 will be 4.9403. So the result of their difference will be given by this. It's 0.0597. Also, the change in time, if you look at it, the change in time, as you can see, because I'm wondering what's going on between 0.99 and 1, the change in time will be 1 minus 0.99, right? Which will give us 0.01 seconds. So you see, the number is between here, in this case, if we look at this, you see the numbers here are even closer. Look at, previously we considered these numbers, 0.9 and 1 second. Now we'd like to see something even closer to 1. So keep in mind we got this result, 5.7. And now the same thing, we will do the same thing here. So the average velocity, so the change in position over the change in time, will be nothing else than just the quotient of the two. So this will be delta s over delta t, which is the first result, which is 0.0597 over 0.01 seconds. And we obtained this result here. So this will give us 5.97, right? All right, let's compare this with the previous result. What do you see? Can you tell me? You see, it's something we get approaches 6. Very, very good observation. As we get closer around 1, the average velocity will approach 6. That's great. So this is what, well, more or less, in other words, what that limiting process is all about. So let's do something even better. Now let's see what happens between 0.999 and t equals 1. And let's see what do we get. And we'll get something even closer to 6, sorry. So look at these two guys here. And again, we'll do the same thing. The change in the position between these two times, right? So between 0.999 and 1, right? Between these two times, the change in the position will be s of 1 minus s of 0.999, which is 5 minus, so keep in mind, you just replace t equals 1 and t equals 0.999. So it will give you this here, right? The same thing, well, the change in time is quite clear, 0.01 second. So the quotient, the change in position over the change in time, which is delta s over delta t, will be nothing else than just 0.005997 over 0.001. And this will give us 5.997. So it will give me something even closer to 6. Well, what we just described here is nothing else than just the limiting process. It's nothing else. The only thing that's missing here is just, for me, is just to take the limit. Anyway, I think I did, if you look at the very, very first video that I sent you from last So for the fall semester, right? Well, I'll talk about the big picture of calculus. You will see that I gave a bunch of examples there, very similar examples. So far, I haven't mentioned anything about limit. So the question is, what is the instantaneous velocity? And it looks like the limit is probably 6, right? Because we're getting very, very, very close to the number 6. So we'll see a better way to find this limit very, very soon. Okay. So, but yes, indeed, the result is 6. All right. Let's see some definition. So as you expect, based on the example that we talked about, the instantaneous velocity will be nothing else than just, as we have seen, the change in the position over the change in time. But it's not just that, it's the limit as delta t, as the change in time approaches 0. So that's what you need to know. So that's the instantaneous velocity. So is the limit as delta t approaches 0 of this quotient of delta s over delta t. I would like you to look at it, to photograph this. Exactly. So like William says here, yes, it's 6 meters per second squared. Yeah. Yes. So I would like you to look at this formula again. Because it will be very important for future purposes. So once again, the instantaneous velocity is nothing else than the limit as the change in time goes to 0. So in our case, we'll denote this by delta t of this quotient, the change in position, which is delta s, over change in time, which is delta t. So that's the formula for the instantaneous velocity. Anyway, you will see that this is nothing else. We would like to see now how is this related to the derivative. So far, I haven't mentioned the derivative yet. As you can see, I just played a bit intuitively without any derivatives yet. All right, now let's see another application. So I see a question. So once you take the derivative, it will give you the speed. So that was the question that was asked. Yes, exactly. We'll get there. I don't want to jump, but yes, like the answer to William's question is yes. But anyway, we'll get there. So far, let's just play with examples. So once again, this is the formula. You'll see that this is nothing else. Well, if you brought it up, this will be nothing else than just the derivative of s with respect to t. But anyway, let's see another application. A biological application. So the population of tribbles in thousands on case 7 is given by this function. Again, we'll have the same function, the same position function. Well, we'll call this now, since it's a biological application, we'll call this a population function. So it's p of t equals 3t squared plus 2. So this is our function where t is the time in days since the infestation began. First, the growth of the population at the end of the first day looks like this. Wow. Well, it's kind of what you expect. So this is the graph of P of t. The graph of the population function. And let's not forget the fact that the population function is a quadratic function. So it's 3t squared plus 2, right? So this is the graph of the population function. Okay. So that's, and like I said, we would like to find the growth rate of the population at the end of the first day. The growth rate at the end of the first day. So how we should proceed for this? So we would like to estimate the growth rate. So at the first day, so we like to see what happens around the first day. So between t equals 0.9 and between t equals 1. So we have this population function, which is P of t equals 3t squared plus 2, right? And we would like to estimate the growth rate. So we would like to see that we see that the change in population will be P of 1 minus P of, just like we have seen before, minus P of 0.9. The only difference is that I'm denoting, now I have the population function of t. Before we had the position function. So it's P of 1 minus P of 0.9, which is 5 minus 4.43 thousandths. So this will give us 0.57 thousandths. All right, that's the change in population. We like to see now the change in time is just 1 day minus 0.9 of a day will be 0.1. Well, guess what? Now, as we have seen before, we're going to take what? Can you tell me? How are we going to estimate the growth rate? The limit as x approaches 1, but let's not talk, okay, but okay. So it will be the limit as x approaches, or t, or not x, maybe t. Right, Jonathan? You meant to say t, not x. So yes, so, and we will take the change in population over the change in time. Exactly like Mason says here. So it's 0.57 over 0.1, correct? So the change in population over the change in time is delta P over delta T, which is 5.7 thousandths per day, right? Okay. All right. So now let's look even closer. Let's estimate this a bit closer. So what happens when we have between t 0.99 and t equals 1? Again, we'll do the same thing. The change in population will be P of 1 minus P of 0.99. So this would be 5 minus 4.9403, which will give us 0.0597. Just remember that we have this function over here. That's the population. Oops. Oh, my pen is out of battery. So let me just charge it a bit. That's why that doesn't write anything. So once again, Keep in mind that what the population function is. P of t is 3t squared plus 2, right? So the change in population will be P of 1 minus P of 0.999, which will give us, if we just do elementary algebra, this will give us 0.0597 thousandths. And now the same thing we'd like to see for the change in time. So the change in time will be 1 day minus 0.99 days. So it will be something even closer to 0, sorry, 0.01. And now the same thing, the change in population over the change in time will be delta P over delta T. Delta P is 0.0597 over delta T, which is 0.01. And if you divide these two, this will give us 5.97 thousandths per day. Well, let's compare a bit the results. So let's compare the results a bit. So you see here, 5.97. And if I go back, so if here is 5.97 when we had these two here. Between 0.99 and 1, so we got this here. And now between 0.9 and 1, we got this here. Oops. Well, you see that this the second one is more accurate, but as if I, for example, I have a question now. Now, if I go even a bit further, and if I consider between t 0.999, now I add another 9, and t equals 1, what do you think the ratio between change in population and change in time will be? Can you tell me? What will be your hunch? What do you think is going to happen? I'd like more people to answer. So what do you think is going to happen? So it will be 5.997 indeed. Yeah, like Nolan and Matt say, both of them say, this is what is going to happen. So we'll get something even closer to 6. So that's what we're getting, right? Yes, approaching 6. Correct, Frank. Yeah. So now, as you have seen, let me tell you the picture. Again, you see, just like you already said. So again, between these two times, we'll get this. So that will be the change in population. And change in time will be this. And again, if we will get this. 5.9997, just like you said. Yes. Well, what you can, and what you, so yeah, you already said it's approaching 6. So in other words, we're just taking the limit as delta t approaches 0, and this will approach 6. But anyway, this is just intuitively how how to play with this, right? Okay. In other words, what can we say? Growth rate is exactly the same idea as velocity. So when you hear the word growth rate in biological populations, right? And I believe you will hear this, and if you take any a biology class or whatever, math biology, it will be the same thing as you have seen in physics with velocity. So both of them, both growth rate and velocity, will involve derivatives. So both of these will involve what we'll call derivative. So far we haven't called it yet, but it will be, you see, the limit of that difference quotient, right? The change in position over the change in time. Delta P over delta T, right? So this would be something like the lim as delta T approaches 0 of delta P or delta S or the limit as delta T approaches 0 of delta P over delta S. So this guy, the velocity goes here and the growth rate will go here, right? So that's the word we're looking for at this point. We'd like to see what are the derivatives all about. All right, so summarizing what we have discussed so far, that's exactly the picture you need. That the growth rate is the same idea as the velocity, and both of them will involve the limit of the quotient, as where on the top you will find delta, the change in position or change in velocity, and on the bottom you'll have you will find a change in time. Here I made a mistake, sorry about that. Here's delta t, right? On the bottom you will always find delta t. Okay, so I'd like you to look at this picture, to keep this in mind. All right. Do you have any questions so far? Is everything clear? Did I go too fast, too slow? So it's okay, all right. Please stop me at any time when you do have a question. You know, when you have slides, it's always this temptation to go a little bit faster because you're not writing in real time. So you're just basically reading, and you're gonna write overwrite. You'll write over the slides, right? So you have this temptation to go a bit faster, but I hope that's not the case. So if I go faster a bit, please stop me without any hesitation. All right, so keep in mind this picture. Like I said, we haven't mentioned what the derivative is yet. Well, actually I said it, but I shouldn't have. All right, now let's talk about the slope. So the slope of a line is what we say the rise over the run. Right? We can have a line and we can write this in slope-intercept form. So for example, a line you say y equals mx plus b. So this is in slope-intercept form. Right? Where that m there, if we look at this guy m, this guy here is nothing else. This is actually the slope of the line, right? We'll denote this, let's say m, and we have this formula here. So it's delta y over delta x. So in other words, we can say that this is y minus y naught, right? For a certain point on the line of coordinates x naught, y naught, the slope will be nothing else than just delta y over delta x, or you can say it's y minus y naught over x minus x naught, right? So that's the slope. Keep this in mind, is rise over run, delta y over delta x. Okay, because we're getting there, we're getting very close. And now let's see, it will make sense to talk about the slope of a tangent line. Okay, so imagine we have the graph of this function. Well, this looks like a similar graph that we have previously seen, right? It's basically like this, the graph of a quadratic function. And suppose we have a point P there, right? Coordinates x, f of x. Well, it doesn't really make sense to talk about the slope of a graph that's not a line, but we can talk about the slope of the tangent line. So this is important here, because now when we talk about the slope of the tangent line, this is how we're going to define the derivative. So keep this word, the slope of the tangent line. So this is what we'd like to talk about. But first, let me just say that the slope of the tangent of the secant line, right, is nothing else than just rise over run. So it's delta y over delta x, which delta y is f of x plus delta x minus f of x, everything over delta x. So that's the slope of the secant line. And now let's see what the slope of the tangent line is. And the slope of the tangent line will be, look at this, look at both of them and try to spot the difference. So what is the difference between these two? Can you tell me? So what is the difference between the slope of the secant line and the slope of the tangent line? Indeed, yes. Yes. Like Frank, Jonathan, and Mason say is the limit. So the difference between these two is this guy over here. Look at this guy. Is the limit as delta x approaches 0 of delta y over delta x, right? So if we take the limit of the secant line, we obtain the, if we take, sorry, the limit of the slope of the secant line, we will obtain the slope of the tangent line. And let me just look at this picture. You see the secant line here between P and Q, right? So I have P of coordinates x, f of x, and Q of coordinates x plus delta x. So I'll add a little bit more. So Q will be of coordinates x plus delta x and f of x plus delta x. And now I would like to see what happens when delta x is small enough. So when delta x is small enough, in other words, when Q approaches P, so it will be very close to each other, this is how we will obtain the slope of the tangent line. And this, in fact, at this point, probably now, putting everything together, you can say that this is nothing else, is related to it's nothing else than just the derivative, basically. Okay, finally, it took us quite a while, almost an hour. And now we can finally define what is the derivative of a function in a more general setting. So the derivative of a function y equals f of x, as you can see, is nothing else than just, we will denote it in this way, f prime of x, right? or we can also write it as dy over dx. And this will be nothing else than just the limit of the difference quotient. So in other words, let me write it again. So the limit, let me write it with a different color. Okay, this. So the limit as h approaches 0 of f of x plus h minus f of x over h. So this guy here is nothing else than just the derivative of f at the point x. So this is this guy here. And let's put this separate here. So that's the derivative of f. Of the function f. Let's write it in this way. And this guy here, this limit here that you see, this is nothing else than just the limit of the difference quotient. So both of them are equal. So that's the definition. And also see it here as well. I'd like you to stare at this for a bit. This is very important. Right. So you can compute derivatives of functions. You can play around. I think you have something like this in the homework, a couple of them in the homework. Basically, it says compute the difference quotient, take the limit, and this will be for a particular function. And then by doing so, you will get nothing else than just the derivative of a certain elementary function. Anyway, we'll see examples. For example, I want you to look at this guy. So using this definition, and I would like you to think of this example. So using this definition, find the derivative of f when f of x is 1 over x minus 4. So I'm going to give you a couple of minutes to think of this. So you have the definition here in front of you. Try to think in advance, and then we'll discuss it. So there will be some computations here. So So what do you think? So what is the derivative? So if we look at the definition, right? We will say that, in fact, let me write it here, f prime of x is nothing else than just, let's look very carefully here, is the limit as h approaches 0. Well, this is actually the hard way of doing the derivatives, but so far we only have this definition. At some point we will see that there, you will learn what are the derivatives of elementary functions. But anyway, so by the definition, this is the limit as h approaches 0 of this difference quotient, f of x plus h minus f of x, everything over h. All right, and now we're going to replace this, and let's do so. Oh my, this is going to be some work. And there we go. Look at this guy here. Right? This is nothing else. This guy here. Yes, exactly. Matt says, yeah. Something like that. We'll see. So this guy here is f of x plus h. And this guy here is nothing else than just f of x. Right? So by doing just algebra, so we will have that, well, we will work on the top. So we will have that this is 1 over whatever, the difference. So on the top, by having the same common denominator, we'll have this. And guess what? This will give us some point, some things will just cancel, right? You see, we have the same common denominator here. I would like you to look at it. Look, this guy here is the same as this guy here. So it's a common denominator. So of course, when you have the common denominator, you'll have that x, the numerator, we're just going to subtract those. So it will be x minus 4 minus x plus h minus 4, but the minus in front of the parentheses will change the sign. And as you can see there, we just canceled, and we will just have negative h. But this negative h here, it will cancel with this one here, because keep in mind, look at this. And the final result will be nothing else than just this guy here. This is negative 1. Anyway, at this point, there is we don't need to do any more algebra. We obtain that the difference quotient. So this guy here will be nothing else than just this guy here. After all these computations that you see. So now the only thing that's left for us is just to take the limit as h approaches 0. And by doing so, we will have that this is, well, we just replace h by 0. And the result, the final result will be negative 1 over x minus 4 squared. So that's the final result, right? So it's just algebra. Using the definition, basically, it's just this is just algebra. Right? Is it clear for everybody? Any questions regarding this, or? So you just replace. You want to see who basically, if you want to compute the derivative, you take the limit as h approaches 0 of the difference quotient. On the top, you have f of x plus h minus f of x. On the bottom, you have h. No problem with h. The only thing you need to work on is just it's on the top, on the numerator. And you just replace, since you know who f of x is, you know who f of x plus h is, you replace them and try to do the algebra. And basically, at the end of the day, once you do the algebra, at the end, you will take the limit as h approaches 0, and then you'll get the result. That's the philosophy. It's pretty straightforward. All right. Now, with that being said, well, let me give you another example, and probably after this other example, we'll stop here for today. We'll continue next time. What about this one? Find dy over dx if y is square root of 2x plus 3. What is dy over dx? Can you tell me that?
Derivative.
It's a derivative, right? It's nothing else than just this guy is y prime of x if you want. So in other words, we need to find the derivative. So find the derivative of this function. That's what we need to do. It is just x. Not quite. So what would you do here? You see, you have a square root, the situation 2x plus 3, and no, not quite. Will be something involving 2x plus 3, I agree. But since we have a square root, maybe it will involve a square root. So. 1 over, let me see. It's, what is s there? 1 over square root of s, what? Okay, all right, so it's 2x plus 3. Yes. With that, I agree. Yep. Well, Eric, let's close, something like that. Nope. Matt, it is something related to that. Well, the result, in fact, I would like you to tell me more options. Yes, Abdul, you're right. All right, so the result will be, let me just spit it out. The result will be 1 over square root of 2x plus 3. Well, here, let me just say, say the philosophy of the how to compute the derivative of this, and then we'll do it next time. So again, by just using the definition, right? So you have to use the derivative, right? Y prime of x will be nothing else than just the limit as h approaches 0 of y of x plus h minus y of x over h, everything over h. So again, we need to work on the top. We need to see who y of x plus h is, so, right? So we'll denote it by this, and it will be this. dy over dx, and well, you can let y to be, you can work with y of x, but anyway, we can also say that if y equals f of x, You can just replace y by f if you want, it doesn't really matter. What matters is that the derivative of y at x is that is the limit of that difference quotient. And now this guy here, f of x plus h, is this guy here. And this guy here, f of x, is this guy here. All right. Now, before we wrap up, what can you tell me about this? About the quantity at the top of the fraction. So what can you tell me about that difference of square roots? How we can because you know, if you replace h, if you take h to be 0, right? If as h approaches 0, you'll get 0 over 0. So what did we say? How to overcome this main difficulty here? What should we do? Congregate? Well, it's called conjugate. Exactly. It multiplied by the conjugate, so it's the conjugate. Anyway, that's what we need to do. And once we do this multiplying by the conjugate, and then we'll do the algebra, but anyway, we'll continue with this the next time. You will see that we will obtain the derivative of this. All right, guys, I will stop here. So next time I will see, we will continue with this example, and we'll also see a bunch of other examples. You will see how to find the equation of a normal line, or how at a point, and so on. Anyway, I'll stop here. Thank you very much. And by the way, I will expect you to come to my office hours if you have any questions. So my office hours will be in like 30 minutes. So please stop by. The link is different. This is my personal ID meeting, right? Okay. I'll see you. Take care. Bye-bye.